Welcome back, Physics 30. This is the MP1.1, the first section for the MP1 section, reference frames and postulates of the special theory of relativity. So in this section, we'll be looking at what is meant by a frame of reference and distinguish between an inertial frame and a non-inertial frame of reference, and then talk about the 2 points or two postulates of the special theory of relativity. So first of all, frame of reference. Any measurement of position, distance, or speed must be done with respect to some reference or reference frame, reference area, which we refer to as a frame of reference. So for example, if you're on a train traveling at 80 kilometers per hour this way, so let's say our train is moving this way, and a person right here is walking at 5 kilometers per hour. What could you say? So this 5 kilometers per hour is the person's speed with respect to the train. So as its frame of reference. So with respect to the ground, if someone was standing out here and watching this person and watching the train, it would be 5 kilometers per hour plus an 80 kilometers per hour. So this person would see that person going 85 kilometers per hour because those velocities are additive. They get added. Whereas these people right here, according to them, they're at rest and they just see this person walk by at 5 kilometers per hour. So these people here would say, oh, we see the guy move 5 kilometers per hour to the front of the train. And this person would say, no, I see the person moving 85 kilometers per hour running towards the front of the train. So it is always important to specify the frame of reference when stating speed in everyday life. We usually mean with respect to the Earth. So usually our observations are with respect to the Earth. And we kind of consider the Earth to be not moving, right? So everything is moving with respect to the Earth, which we kind of assume is not moving. And that becomes important when we're talking about inertial frames of reference here. So each of those is right because they would say they do see him going 5 kilometers, he sees him going 85. Both are equally valid. Now if we look at inertial frames, those are special frames that we're going to see here. If your reference frame is an accelerating car, an object such as a cup resting on the dashboard may begin to move towards you. So if you find yourself in accelerating frames that are speeding up or slowing down, things are weird. So you have flying coffee cups flying all over the place, backpacks that are moving, Kleenex boxes that are flying. So in accelerating vehicles, the objects that were in motion stay in motion if you're slowing down, so they appear to fly forward, or objects at rest stay at rest. If you gun it and you're accelerating fast forward, everything that was at rest and not tied down will be moving backwards, appearing to you. So the cup accelerated towards you, but neither or anything else exerted a force on it in that particular direction. So that's weird. Similarly, in the reference frame of a decelerating bus, there's no force pushing the objects forward, even though it appears that all of a sudden objects are flying forward. In accelerating reference frame, Newton's law, his first law, does not hold. So remember, Newton's first law was that an object at rest wants to stay at rest, or an object in motion will stay in motion in a straight line with constant velocity. Those will not work if you're accelerating. For example, a cup that was at rest, if you step on the gas and go forward, that cup comes flying backwards and it seems weird to you. Why is that cup flying backwards all of a sudden? So Newton's first law does not hold in frames that are accelerating. So physics is easier in reference frames in which things are at rest or moving at constant velocity. So Newton's laws do hold true in what we refer to as inertial reference frame, where the laws of inertia, things at rest staying at rest, and things in motion staying in motion at constant velocity, happen. For most purposes, we'll usually make an approximation that a reference frame fixed on the Earth is an inertial frame. Because technically on Earth, we aren't in an inertial frame. The Earth is spinning, right? And we know that we would want to fly off tangentially, as we talked about. But since the Earth is so big, it appears that to us that it's not moving. So for all of our intent and purpose, we are not moving, and it's an inertial reference frame. So if I'm at rest or at moving, I should get the same result. So it's partially due to the Earth's rotation, but of course we can make that assumption. Einstein's special theory of relativity deals with objects, how we observe events, particularly how objects and events are observed in different reference frames. This subject had already been explored by Galileo and Newton. The special theory of relativity deals with events that are measured in inertial reference frames. So frames that we are used to moving. So if we're using Earth as a reference frame, that's like saying, oh, all this is happening when we're at rest and we're looking at events moving. Or if we're moving at constant velocity, we would in fact see the same type of results, as we'll see. It is usually easiest to analyze events when they are observed and measured by observers at rest. And usually that's how we do. We look at a car moving by us and we say, oh, that car is moving 50 kilometers per hour. And in our mind, we're thinking of it as 50 kilometers per hour in reference to our fixed point. The Earth, though not quite inertial frame, is close enough for it to be at rest. Rotating or otherwise accelerating reference frames are non-inertial frames. We'll discuss those later. So that's in MP1.1. And there's some interesting things that happen with accelerating reference frames. So a reference frame that moves with constant velocity with respect to an inertial frame is also inertial. So it all relates back to Newton's first law. Object at rest stays at rest. Object in motion stays in motion with constant velocity, straight line. We would get the same results whether we're at rest or if we're moving at constant velocity, as we'll see. When we say we observe or make measurements from a certain reference frame, it means that we are at rest in that reference frame. Now, both Galileo and Newton were aware of what we now call the relativity principle applied to mechanics, which states that the basic laws of physics are the same in all inertial frames. So frames that are at rest or moving at constant velocity. So for example, objects move in the same way in a smooth, constant velocity train as they do on the Earth, or a train that's at rest. Now, smoothly moving, we have to make a big assumption there. We assume there's no vibrations or rocking that makes it non-inertial. When you walk, drink a cup of soup, play pool, drop a pencil, or do anything, and when you're moving at constant velocity, you get the same results as if you were just standing still on Earth. So if you throw a ball up in the air in a room, you catch it. If you were in a van that's moving at constant velocity and throw a ball up in the air, you catch it because it's not accelerating or decelerating. You and the ball are moving at the same speed. And we talked a bit about that in our projectiles unit. So suppose if you were in a car traveling at a rapid constant velocity, if you drop a coin from above your head inside the car, it falls straight downwards with respect to the car. And that's logical. It hits the floor directly below you. All right, so that makes sense. You drop the coin, it falls down to the floor. This is just how objects fall on the Earth, straight down. Thus, if you were standing on the road and you drop a coin, it goes straight down. So you are at rest. And if you're moving at constant v, so if you're moving at constant v and drop a coin, it falls straight down too. So that shows that both of those reference frames, you would see the same thing happen. You'd see it fall straight down. Now, if you were speeding up or slowing down, you wouldn't see the same thing, but we're talking about inertial reference frames here. If you drop the coin out the window, though, of course, this won't happen because air drag would appear to pull the coin backwards. Note in this example that to an observer on Earth, the coin follows this path. So if you're dropping it, you see it fall down, but this person sees it go to the right. And you've seen this before. Falls down, falls down. So the person in the car sees this, the person on the ground sees this. And remember, with projectiles, they have the same time of fall. So we're going at constant speed and it would cause a curved path. So the actual path followed by a curve is different as viewed from different reference frame. Now, this does not violate the relativity principle because this principle states that the laws of physics are the same in all inertial frames. The same law of gravity and the same law of motion applies to both reference frames. The acceleration of the coin is the same, so the time of fall would be the same as we saw. The laws of physics therefore predict that it would follow a parabolic path like any projectile. In the car's reference frame, there is no initial velocity, and the laws of physics predict that the coin will fall straight down. And therefore, we would say that the laws of physics apply in both. Like if we launch something horizontally, yes, it follows a curved path. So the person outside on the ground would see that. The person in the car sees it, oh, I'm at rest, therefore it falls straight down. Both of those reference frames are good. All right, I'm going to stop right there, and then in part 2 we'll come back and look at the rest.